All right, so we'll take a look at our, this is a bit of a review for the solubility and acid-base exam. And I just kind of went through the notes and highlighted some of the important things that we covered. If you have questions, please ask. But I'm just going to kind of go over and just talk real briefly. I left space there for you to write notes and examples, diagrams, whatever you need to do to study. I would suggest that making a study sheet like this before an exam would be a great idea. Some of you already do that. Some of you maybe just read over your notes. Some of you just touch your textbook and think that's studying. I'm not really sure. But to make notes like this, to make a summary page with all the important stuff on there, especially things that you're unsure of, that you can read over and study and just get ingrained in your head before the exam, is a great thing to do. So here's an example of a outline for you that you could go through your notes, go through the textbook, jot down things that I've said during a lecture or whatever that you wrote down that's not in the notes maybe, or not in the textbook, or a diagram that you've researched online, or whatever. Put it all together and really ingest it before the exam. So just to kick off, I will refer back to the notes and show you the notes a little bit, but you can also have your notes out and open. That would probably be a good idea, so that you can kind of go through this, either highlight or check out what I'm saying here. Make sure you've got it in your notes. Make sure you've got the blanks in the notes completed. Make sure you've got your homework questions that are associated done, those kind of things. So as we go through this review, I want you to kind of check off the boxes, ask the questions that you want to ask, and this is a good way to prepare for a unit exam coming up. Okay, so one of the first things that we talked about and what we did was we talked about acids and bases. Now I do have, this is not necessarily in order. We did solubility a little bit before acids and bases, but some of these outlines they're not exactly in order. So if you're starting with your notes, we did solubility first, talked about KSB first, but I do mention this in the outline a little bit later. So some of the important things you need to know, the theories that we studied. We studied the Bronsted, Lowry theories, the Arrhenius theory for acids. We talked about basically, and I didn't write this down, but what are acids, what are bases, what are some characteristics. You can certainly jot that down. So as I add to this outline as well, the theories are important, right? You also might want to, characteristics, right? That's a bit of a given, but characteristics of acids and bases. And of course that leads into the theories, right? So the Bronsted-Lowry theory, I guess the Arrhenius theory was sort of the first one, right? That acids release hydrogen ions, bases release hydroxide ions into solution. Bronsted-Lowry came along and adjusted that just a little bit and said, you know what, some bases don't have OH, so bases cause OH to be released in solution, but it doesn't necessarily come from the base. And that's the big difference with the Bronsted-Lowry. And let me just get to your notes here. So the notes here, we talked a little bit about what acids and bases were, what they looked like, characteristics. And then we launched into these theories right away, okay? So these theories right away. So releasing OH and H, Bronsted-Lowry, shifted the focus to protons, right? So proton donors, proton acceptors. Acids are proton donors, bases are proton acceptors. And bases, by accepting that proton from the water molecule, releases the OH ions from the water molecule. So you'll want to make sure you go over that and have a good understanding of that as well. I'm just going to move this review up a little bit higher so it's a bit easier to access. And certainly if you have any questions, let me know. So the theories, make sure you got those figured out. Basic characteristics of acids and bases. All right. Hydronium hydroxide ions. Okay. So that's a little small for you in the back, but hydronium. That's something new that we talked about. And of course, with these theories, you have to know that hydronium is H3O+, right? That is roughly equal to just writing an H+ ion. And in your textbook, and in some cases, we do just talk about the H+ ion, okay? Because the hydronium ion includes a reaction with the water molecule. And sometimes that's just kind of left out in some of our quick notation. So these are roughly equal. Hydroxide ions are, the OH- ions, right? That's hydroxide. So please know the difference between hydronium and hydroxide. And of course, the measure of acidity, right? And we'll get to pH a little bit later, but the more hydronium or hydroxide ions there are in solution, the more acidic it is, acid. The more acidy, right? And the more OH ions in solution, the more basic it is. So you want to know the basics there about acids and bases. So you will remember as well that we talked about in our notes identifying conjugate acids and bases, right? We talked about what a conjugate was. Conjugate acids are what the base becomes, and conjugate bases are what the acid becomes. So in this example where we have HCl reacting with water, okay, HCl clearly is the acid. We all know that that's a really strong acid. So if you're wondering about HCl, what that is, you do need to do some more studying right now, because you should know that's hydrochloric acid, and that's very strong. It dissociates readily and quickly. And so it's going to give its hydrogen to the water to make H3O+. So what the water is the base here, and what the water becomes is the conjugate acid. What the acid becomes is the conjugate base. So you should be able to identify these in a reaction, okay? And of course, conjugate, it means the same but opposite. So if this were to go back this way, then this would be the acid, right? This would be the acid, because it's going to donate this extra proton to make HCl over here. So donating a proton makes it an acid. So acid, a base becomes conjugate acid, and so on. Any questions there? We good? You should be able to identify those clearly given an equation. All right. So identify acid base, conjugate base. Okay, so the Ka and the Kb. Obviously, I'm starting with acid material here, this acid sort of section. But Ka and Kb and Ksp are very similar. All right. So remember Ksp. Let me just go back to Ksp a little bit. If you have a Ksp equals something like, 1.0 times 10 to the negative 8. Okay. So this is a relatively low Ksp. Remember we said anything under 10 to the negative 4, anything less than that's pretty soluble. Anything above that starts to become less soluble. Anything below that is not soluble, and anything above that becomes more soluble, my bad. But the Ksp, remember, is the solubility product. We don't add them, we multiply them. And what do we multiply? The concentrations of the ions, right? And so because we know what Ksp is, Ka and Kb are very, very similar. Ka is like the solubility product constant for an acid. Kb is like the solubility product constant for a base. So let me just see here. Where do we get into Ka? So these obviously, these notes here you have, or you'll be able to watch a video if you need to, but here's where we talked about Ka and Kb. Very similar to Ksp. So if you look at this little chart here that I have up on the screen, if you guys want to shut the lights off, you can. It might be a little bit easier to see. I'm not really sure. If you want to do it, does it matter? So for HCl, for example, right? HCl breaks up into H plus and Cl minus as a dissociation equation. And the Ka would be the product of this concentration of this ion times the product of the concentration of the Cl, right? And so because this Ka is super, super large, it's much, much greater than 1. So that means that we have a strong acid and we have an abundance of ions here. So this is, the concentrations are very, very high. Strong acids. Once we start getting down into these values of Ka, like, down here, let's say, so benzoic acid here, this breaks up only slightly. And just like Ksp, you can use this number to determine how many ions or what the concentration of these ions are in solution. Remember, a weak acid only breaks up partially. There's some of the original acid molecules still intact, and there's some free ions floating around. So because this is, there's only some of these that it's a weak acid. Here, up here, notice that the arrows are just one way. So HCl completely dissociates into this. So it's like HCl is virtually gone, and all that's left over is just the ions, right? Okay. All right. So if I give you the KSP, let's go back to KSP. If I gave you the KSP for, let's just say for AB2, let's say, and this is a made-up compound. What you would have to do, if I asked you to find the concentrations of the ions, right? I don't know if you have room to write this down here or if you just want to watch, but concentrations of ions given KSP, well, we could do that. What you have to start with first is the dissociation equation. So obviously this is a cation, and we have A. Now we have AB2, so we could say, you know, this is what happens, right? 1A to 2 B's. This is probably a plus, and because there's 2 B's attached, it could be a +2. So I'm going to give you this, and this is a fictitious compound, but this is what the dissociation equation would look like. And you're going to need to write this first. Why do you need to write this first in solving a question like this? Because we have the KSP, which is the product of the concentrations. So we need to let the concentrations of these ions equal some unknown value like X. This is what we've done in class. So for example, we're going to have X here, 1X here, and we're going to have 2X here. So if 1X moles here of this breaks down, it's going to give 1X here and 2X here. All right. Now, this is actually going to be a dual reversible reaction. So because this number is pretty low, so it's a weak acid, looks like. But we're going to find out what this X actually is going to be. Okay. So what we do from here is we understand that the KSP for this kind of thing is going to be the concentration of A2 plus, or A plus 2, times the concentration of B minus, that's going to be squared. Remember, with that coefficient there. So to fill that in, we go 1.0 times 10 to the negative 8 equals, and this is a 1x here, times, now the B is 2x. So remember, yes, 2x and squared, because that's according to the KSP. So hopefully this is bringing back some memories for you. And I guess just as I continue here, this is going to be 1 times 10 to the negative 8, and this is going to be 4x cubed. That's supposed to be a 3. We divide by 4 both sides. We take the cubed root both sides, and that will give us our x. So we could find what x equals, and that x is going to equal, of course, the concentration of A2 plus, for example. Okay, so let's just do that. Let's take the cubed root of 1.0 times 10 to the negative 8 divided by 4. That should work if I type it in like that. Let's see, 4 cube root, okay, 0.01357. X equals 0.01357. Somebody can double check that math here, make sure that worked out, you agree with that. But if this is indeed the exact value for X here, then we know that this is the concentration of A. Okay, that's the concentration that yields this KSP at this temperature. And then of course we do 2X will give you the concentration of B. All right. Now I'm going to just skip this right now. I'm going to jump actually right down to this point because this leads me into this point. Okay, so I chatted with a student yesterday about this, and this is something that's really important to know. You can find the concentrations here, but also if you're asked a question like this where you're asked to find the solubility of the compound, you can use the KSP to find the solubility of the compound. So solubility given the KSP, this X right here, it is a concentration for A. It's half the concentration for B, because we'd have to 2x here to get B. But also notice this. It's also, this X also is associated with this AB2. You see that's a 1-to-1 ratio. So what does that mean? It means that this is also the solubility of the compound. 0.01357 moles per liter of AB2 will dissolve to make a saturated solution. So that's the solubility as well. This is the solubility. So you find the solubility the same way that you find the concentrations of the ions given the KSP. Okay? And again, if you guys have questions, more questions about that later, you can ask me. Okay. Now there's a little note here too. I'll just finish this point before I go back up to the pH knot. But the solubility, I could ask you for solubility in moles per liter, which would be like the default here, moles per liter. But I could also ask you in grams per liter or grams per 100 milliliters or something. So grams per liter would mean that you would have to convert moles to grams. And we learned that some time ago, last year. Moles to grams, you look at your periodic table, which I will provide you a periodic table for your exam. But moles, remember our little chart there, moles to grams. What do you do? How do you get from moles to grams? How do you convert that? Anybody? Shout it out. How do you convert moles to grams? Multiply by, yes, the molar mass of the substance. Very good. And which is the grams per mole, right? The conversion is pretty easy between grams and moles. It's times grams per mole, going this way. So yeah, so what you would do is you would look at your periodic table and find A, whatever A is, and you would add 1 mass plus 2 masses of whatever B is on your periodic table. And that's the grams per mole. So you would take this number and you would multiply by the grams per mole to get grams. So be aware, you may have a solubility question like that. Okay, any questions about solubility KSP, Ka? Ka is done the exact same way, really. If you're trying to find the concentration, let's say A, if this was Ka, this concentration of A would be H+. Once you find that concentration of H+, then you can find pH. So using Ka to determine pH is something that we've done and you're going to need to know how to do. It's performed exactly the same way that you would find concentrations for a solubility or for KSP. pH, remember what pH, or what the P stands for. The P is the negative logarithm, and then the H means of the concentration of H+ or hydronium ion, interchangeable there. So if this were the concentration right here that we determined and this was a Ka instead of a KSP, then I'd put this number in right here. And I would literally on my calculator do negative log this number equals. That's your pH. So what is the pH here? Well, let's figure that out. So negative logarithm 0.01357 is 1.867. 1.86 or 1.9. So is this a fairly acidic or fairly basic solution here? If that pH is low, it's really acidic. Yeah, very good. So it's very, very acidic. And if you look at this concentration, that's actually a pretty high concentration for H+. And we'll talk about the Kw a little bit in a few seconds here. But the POH is the negative logarithm of the OH concentration, okay, if you're given that or if you can find that. So remember, if you have something like a strong base, NaOH, that's going to dissociate to Na plus OH minus, right? So if you're given a concentration, let's say of this, because it's strong, it's going to completely dissociate, so it's a 1:1:1 ratio. And you will be able to identify the actual concentration of these ions. So if I give you 0.2 molar NaOH, how many OH ions do you have in that solution? 0.2 molar. Okay, because it's a strong base, it completely dissociates. So if you're given a concentration of OH, you put it into negative logarithm of that number and you get the POH. Okay, KW. I'm just gonna erase here some of this stuff now here. Apologize, but hope you have that down. If you don't have it down by now, you probably didn't want it down. So I am going to focus on KW now, and KW is sort of where we started before we even got into KA. But KW is it's 1.0 times 10 to the negative what? Like I heard somebody say something, I didn't hear what you said though. It's 14, I don't know if that's what you said. Say nice and loud there next time. I got the air conditioner going here and we all got masks on here still, so say nice and loud. So 1 times 10 to the negative 14, yeah, that's KW. And again, that's just like KSP or Ka for water. So water automatically dissociates into its ions. The product of H plus, right? The product of the H plus concentration plus the OH minus concentration is this number. Very, very small. So that means that water does not release a whole lot of ions. It stays as a water molecule for the most part, but there are a predictable number of ions that would automatically dissociate. Okay? So that's going to be very important because this is the number that we use if we want to solve for one of these. If we want to solve for OH or if we want to solve for H plus, etc., we're going to use that KW number. Okay. pH, this is another one. pH plus POH, what does that equal? 14, very good. And that 14 comes from this, right? Very good. Let's see, if you're given pH and you want to find concentration of hydrogen, if you want to go backwards that way, remember it's 10 to the power of the negative pH equals the hydrogen ion concentration. So whatever your pH is, you do 10 to the power of negative that number. Okay? We talked about that too. So concentration, you can find pH by using the log, and pH, you can find the concentration by doing the inverse of log, which on your calculator you'll see the inverse of log is 10 to the power of x there. That's the inverse. Okay, stop me if I'm going too fast or if you're missing something. Are you guys okay? Okay. I know this has been a while since we did this stuff, so yeah. Okay, so any questions regarding pH, POH, or Ka, Kb, Kw? Okay, so naming some common acids and bases. Remember to study your notes there. You should know how to name binary acids for sure. You should know some names for some common acids and bases. And again, in the notes, I guess in those notes back up here, we talked about some common acids and bases here. There's some bunch of hydroxides, right? Those are strong common bases. And here's a list of some common acids as well. I would suggest you trying to memorize some of these. Hydrochloric, we've used a lot, nitric and so on, sulfuric, hydrofluoric, hydrocyanic, that kind of stuff. Phosphate, right? Phosphoric acid and so on. So study your notes, study this this chart a little bit. You have this in your notes too, I think. Those are the different theories, and we did questions like that. Okay. And here are some notes on naming binary, and you should study some of these common ternary ones that we looked at as well in naming ternary. Okay, and that's where we led into strength of acids and bases, which is your Ka. Okay. Okay, we're almost done. The little outline I have here. So let's just keep going through. Titration. We kind of next went to titrations, and we just got finished a titration lab. So you've done titrations here recently, and you should know a lot about how they're done. In our lab, we started with an acid, mimicking sort of stomach acid. We tested different antacid tablets to see how they would react, and of course, what we expect was the antacid would counteract the acidic levels in your stomach. So if we have a very low pH in your stomach, that those tablets brought the pH up a little bit. Then we performed a titration by titrating NaOH into that solution to bring it up to a certain pOH, which was indicated by a color change in our phenolphthalein indicator. So a titration, okay, you can, and we're not necessarily doing this. This is one of your questions. Like, how much, did this antacid tablet move the pH? You can calculate that. But titrations normally are used to determine an unknown concentration of some kind of acid. So if we have an unknown concentration of acid, if you add base until you get to a certain pH, you know how much of that base you added. You could calculate the exact number of moles of base that are in there. And if the end point of the titration, where the color changes, is the same as the equivalence point at pH 7, then the number of moles you put in of a strong base equals the number of moles of the strong acid. Okay? In your case in the lab, let me just zip down to this diagram here. Okay? So for this lab that you guys did, we used phenolphthalein. So we did not reach pH 7. Some of you on your lab day data and observations are here for you to retrieve there at our break. But some of you said when we hit the color change, that was pH 7. Was not pH 7. It's closer to pH 8 or 9. All right? Now you checked with some of that Hydronium paper or that universal indicator paper. I don't know if that said it was 7 or if it said it was 8 or said it was 9. But at the point where this changes from clear to pink is about pH 8. Really hot pink you would be probably pH 9 or above. Really, you'd probably be above. So what you did in the lab was you got that from colorless until you got a sustained pink solution, then you stopped. So notice that the end point of your titration was here. That's the end point. Okay? Is where the color changes of the indicator. Now sometimes you may use an indicator that has an end point at pH 7. In that case, the end point and the equivalence point would be equal, but not for this lab. Okay, so some of you are going to have to rethink what you said, what your guesses were in your lab day data. But the end point's going to be here 7, 8, 9. It should be about pH 9. That's where this color would change. Okay, so know the difference between end point and equivalent point. What this means for our lab, or for your lab, if I could just talk about that for a second, it means that however many moles of base you put in will not equal the number of moles of acid. They will not be equal. Okay? Because the pH is 9 and not 7. So you have to kind of account for that. And I'll talk a little bit more about the lab maybe after this review, okay? But yeah, I thought this diagram would be good for you to see the difference between end point of a titration and equivalence. If we were using methyl orange, for example, the color would be a dark orange. You see how it's orange on this side of this little color thing? So this is orange here, all the way down, that's orange. And because it's yellow up here, this means that anything above this is yellow. That's what that means. So this indicator changes at about pH, let's see, 1, 2, 3, 4, at about pH 4. So this would be your end point if we use this indicator. Does that make sense? Okay? Okay. All right, so you should have some awareness of the lab, be able to answer questions about the lab, and about generally how a titration might work, okay? Really the last thing we talked about was, we talked about indicators a bit, but buffer as well. So a buffer solution. Remember that a buffer solution can absorb, in a sense, small amounts of acid or small amounts of base, and it can counteract those changes to minimize the change in pH. And one of the important examples that we talked about was the buffer system that is in our blood, right? So we go back to those notes here. In our blood, we're carefully constructed, thankfully, to absorb wild changes in our pH of our blood. And one of the ways that that's accomplished is by having a buffer system here. So I'm just scanning through the notes that you guys have before you. Oh, actually, I should mention that the end point, I should mention this. I was looking at this last night in preparing this. Some clarification, I believe I mentioned this in the teaching, but this could be a little bit confusing between endpoint and equivalence. So let me just clarify this. All right, so the end point of the titration is reached when pH is 7. This, you should know, and I believe I did mention this, but maybe I didn't. Maybe it didn't come across very clearly. I did just mention it now in the review. But this is when the indicator has an end point at 7. Okay, so when the indicator has also an end point at 7. And if you want to add that to your notes so you're not confused, that's fine too. So when, and a lot of indicators do have an end point right around 7 so that you know where the equivalence point is, but not all indicators. So the end point is not pH 7 all the time. It depends on the indicator. So I'll just mention that. I did make those changes for next year's notes, but I thought I'd just clarify that for you guys. So first year of the big change for our curriculum here. Okay, okay, here we go. Obviously, I've changed some things around here. Buffer system. So in our blood is buffered principally by the hydrogen carbonate ion. You should remember that. These equations here show how the hydrogen carbonate ion can accept a proton. Okay, can accept a proton if it gets too acidic in your blood, and it also can donate a proton if it gets too basic in your blood. So this H can go over there. And these products are not excessively acidic or basic at all. We have water, obviously, is the main component there, and this ion gets broken down in your it's hydrogen carbonate. Yeah, so this gets broken down in your lungs to carbon dioxide, which you breathe out, and so on. So these are this is fairly neutral, these products here. So that's the buffer system that we're talking about in your blood. Okay. I should make note in this review that you should make sure you have all of your text questions completed. You should review your answers to those text questions because I've given you those to help you prepare for your exam. And these are the text questions from your Glencoe text. So these are the ones that I have assigned here this year. Okay, Glencoe text, matter, and change. You should have those on your notes sheet. So I can come back to that if you do not have those. But just as we complete here, so indicators. So here's the diagram that I showed you guys. It's in your textbook, in Glencoe text as well. But this is a visual representation of where endpoints would be for certain indicators. So for example, if you had the indicator crystal violet, it would be blue. Everything over pH 1, it's blue. So if you want to know where the pH is next to 0, it's almost a completely dissociated acid solution, you can use this one. It'll tell you when you're at 0 or close to 0. The ones that are really useful would be the ones that are, that kind of change around pH 7, right? This grouping right here. That would, so bromothiamol blue, that should be bromo, by the way. I think that's a typo in the text. Bromothiamol blue would be awesome to find equivalence point because it's yellow here. You see this? When there's a yellow on the end, that means it's yellow all the way here. And blue on this end, it's blue all the way here. And it starts to change color really quickly, yellow to green to blue really quickly, right at pH 7. Okay, bromothiamol blue. We used phenolphthalein. Where's phenolphthalein? Phenolphthalein is right here. Look at where it changes. From white, so it's clear, down here, in acidic, it's clear. And then it changes to pink right here at 9. Okay? Now if you added a lot of drops of phenolphthalein and went over 9, you would get a bright pink, which I know some of you did. Okay? So that's maybe a little bit too much indicator, maybe a little bit too much base. It might have gotten quite a bit darker there. So again, the first point where it changes color and that color is sustained is where you want to stop and do your measurements of how much sodium hydroxide you added. But phenolphthalein gives us an endpoint around pH 9. Okay, it's close to 7, but it's technically 9. Okay. All right. Any questions? Any questions? I think that kind of covers the outline for this exam, this unit exam coming up that includes solubility and acid base. Obviously, there are a lot of solubility concepts used in the acid base. So would it be mostly acid base in that unit? Maybe a little bit more heavy on that than solubility. But any questions? Okay. So there's a quick review on that unit. And yeah, please go over your notes, the textbook questions. and ask any questions that you need to prepare a study sheet, maybe like this one, and be ready to go for the test coming up.